Okay, your Sarai is very good.
So yeah, I can hear everyone very well.
Okay, we will start at 13 and
1:30.
1:30. Okay.
Yeah.
Yeah, before you start, can I ask you, Professor Igor, one question?
Okay, of course.
Is there any interesting oyster for you in Thailand?
แต่อันเนี้ยเรคคอร์ดแล้วใช่ปะ
I think yes, because my Thai colleagues they show me a sample of oyster. It was not very well preserved, but it was definitely oyster. So there is there is interesting samples.
Is that all? I mean, in terms of Holocene age, or maybe a little more older?
I think it was Cretaceous. It was Cretaceous.
Oh. Every oyster is marine or maybe brackish. I don't know. My paleontology work is very bad, so I need your help.
Yes. This is a very good question, because if we speak about modern oysters, some of oysters they are brackish water, and some of oysters they are fully marine. For example, Giatissa or Neopycnodonta, they are fully marine. And Crassostrea gigas, this is a very common oyster which we all know, because sometimes we can see this in markets or in restaurants. It can support brackish water. It can live in estuaries of rivers near the sea. But most of oysters are fully marine, yes.
Okay, let's suppose if we found some oysters within one area, is that indicate the near shore environment, or maybe a little transition or something like that?
This is also a good question. If we, in general, usually oysters they live in near shore environment, but some of them they can survive in deep conditions, not very deep.
Evolution.
Yes, in open sea. For example, if we take recent oysters, Neopycnodonta, this is it can live in depths more than 1 kilometer, so in very high depths. But usual oysters, yes, this is near shore animals.
I think right now our Director General is on the screen, so maybe you can talk to him personally.
Okay. Good morning, Igor.
Good morning.
Okay. What time is it in Russia now?
Oh, in Russia this is 1:13. This is the same time as in Thai and in Thailand.
1:30.
Yes.
Okay. Oh, okay.
In Novosibirsk we have the same times and in Bangkok.
Oh, I see. I think that you are in the western side, so your location is I think is this in the same latitude of Thailand? So we have the same time.
I think not exactly the same. This is just a question of Russian time belts. They're a little bit different than in other world. But yes, I'm in eastern part of Russia, in Siberia now. Yes.
What is the temperature at present?
Temperature, I think around 25 or 30 degrees. This is relatively hot today. Plus 25.
Nice weather.
And in Thailand, in Bangkok?
No sunshine?
Sunshine, yes. In summer, here, this is usually good weather. Usually this is 20 or 25, sometimes 30, even more. The
You
problem
were
is
short in
winter.
the university.
I'm not in university, I'm in institute.
Please.
Yes. University now doesn't work. This is summertime and lessons are finished. Students finish in June, in the end of June, yes.
Okay, I think it's 10 minutes
10 minutes.
before talk. Maybe MC, please.
Because we have announced that the special talk will start at 1:30. Probably there will be some more people come to
Right now,
attend.
totally we have 20. Yeah.
No, yeah. Now we have 10 more minutes before we start, before we officially start. How is the IGCP? Yeah, IGCP project. How is it going? Igor?
Okay.
I heard that you.
About GCP, I think this is a little bit no meetings because of the pandemic, but there is some results, and there is special issue of Cretaceous research where we published some articles. It was also 2 my articles about the stratigraphy of Russian Far East Cretaceous stratigraphy, and about northeastern China, which I made during my postdoctoral research in Nanjing Institute of Geology and Paleontology. So there are some results, and I don't know when we will meet in offline regime, but I hope it will be soon.
Now we have 26 participants already. I'm not sure if I
นะคะมาแล้วค่ะ
ใครเอ่ยมาแล้วค่ะ
เดี๋ยวจะขออนุญาตเกริ่นเลยนะคะท่าน
Yes, you can please. We have 5 more minutes.
ฮัลโหลค่ะ ได้ยินนะคะ
ช่วยเปิดจอด้วยค่ะ
สัญญาณไม่ค่อยดี
สัญญาณไม่ดี not very good signal.
But actually, at DMR, it's very nice.ท่านทิพดีอยู่ที่ห้องหรือเปล่าครับเนี่ย
ครับอยู่ห้องครับผมอยู่ที่ห้อง
เดี๋ยวผมชัดมากเลยสงสัยมันอยู่ข้างหน้าเนี่ยไอ้ตัวรับนี่นั่นนะ
ใช่ใช่ผมใช้ผมใช้โน้ตบุ๊กครับผมใช้โน้ตบุ๊ก
อ๋อ
ก็เลยชัดไปอย่าง use the notebook
สวัสดีค่ะได้ยินไหมคะ
ได้ยินแล้วได้ยินครับ
โอเคค่ะถ้างั้นเดี๋ยวช่วงนี้หนูจะขออนุญาตเกริ่นเลยนะคะท่านคะ
โอเคได้ครับได้ครับ
ค่ะ Good afternoon everyone and good morning Dr. Igor Welcome
not morning afternoon
afternoon okay
we have
good
the same
morning good afternoon everyone welcome to the number 6 of DMR Special Talk of 2021 today we are honored to have a lecturer Associate Professor Dr. Igor Kosenko lecturer from the Novosibirsk State University of Russia for sharing knowledge and experience on the topic Evolutionary History of Oysters and their significance for geological studies. The schedule will start at 1:30 and will be finished at 3:30. The first session is an opening ceremony which will be welcomed by the Director General and followed by a presentation, question and comments, and a closing ceremony. In the meantime, I have 3 points to inform everybody. First, for any participant who have not registered in the Google form, please register now by
ตอนนี้เดี้ยงแล้วครับไม่ได้ยินละ
I think the signal is not very good we have the problem of signal
ได้ยินไหมคะ
Professor Igor can you hear
สัญญาณอินเทอร์เน็ตของหนูจะไม่ค่อยดี
สงสัย
จะมีปัญหานิดนึงโอเคแต่เอาละเอาต่อเลย
ได้ไหมคะ
ได้ละโอเคต่อครับ
Second, all participants, please fill in the questionnaire of this special talk session, which the QR code is I will show it on your screen, or you may click the link in the Zoom chat channel. Lastly, for the question and comment policy, after the speaker presentation has finished, you will be welcome for asking questions and giving comments. You may turn on the microphone or text in the Zoom chat, and I will ask for you. ขอต้อนรับแขกผู้มีเกียรติทุกท่านนะคะเข้าร่วมการรับฟังการบรรยายพิเศษครั้งที่ 6 ค่ะวันนี้นะคะเราได้รับเกียรติ
จะมีปัญหาอินเทอร์เน็ตนิดนึงนะคะของทาง MC
Yes, it got some
ตอนนี้ผมได้ยิน คนอื่นนะครับ
we are not
Igor can you hear
we are not in the same place we are everywhere
Yes,
we are from anybody's home I am at the department I'm at the office
Me too
เอาหนูน้อยหายไปเลย
ชได้ยินไหมครับ
ได้ยินฮะถ้างั้นท่านดี
ครับผม
welcome speed เลยครับ
เอาโอเคได้โอเคตอนนี้
Professor Igor เขาได้ยินป่ะเขาไม่ตอบเลยเมื่อกี้ Professor Igor can you hear me
Yes, I hear you. Yes.
Okay that's good
okay
Sorry.
let me start okay maybe okay Associate Professor Dr. Igor Kosenko distinguished guests ladies and gentlemen Здравствуйте
Здравствуйте.
สวัสดีครับ Good afternoon
Good afternoon. Добрый день.
Yeah. First of all, on behalf of the Department of Mineral Resources, Ministry of Natural Resources and Environment of Thailand, I would like to express our sincere thanks to Associate Professor Dr. Igor Kosenko from Department of Historical Geology and Paleontology, Novosibirsk State University of Russia, for accepting our invitation to be a special guest speaker for the department special talk entitled Evolutionary History of Oysters and Their Significance for Geological Studies. Today, it would be a great opportunity for us to have a good chance to learn about the evolutionary history of oysters in your zone, share knowledge of paleontology, and exchange of view about geology among us. We really do hope that this talk forum will be the first step towards better cooperation between us. And last but not least, I would like to express my heartfelt thanks once again for your kind sharing knowledge and information in today's DMR special talk. Thank you very much. Большое спасибо.
Большое спасибо. Yes.
ขอบคุณครับ
Your Russian is very good.
ขอบคุณครับขอบคุณครับ
Okay, I can start. Yes.
Yes, you can start, please.
Okay, I want to say some words too. I was very happy to have this invitation to this meeting because in 2018 we met in Thailand in IGCP project with our Thai colleague, and it was very well organized, very nice, and very useful meeting where we not only exchanged by our knowledge, but we have new friends and new very good colleagues. And I remember even now all of these days and these field excursions and these lectures and presentations. It was very friendship and it was very, very nice. Like the sun of Thailand, nice and warm and kind. It was very, very good time, and I have very good memories from these days. And now I also say a few words. I did not very long presentation because this year I was very, very busy, not only by geological things, I also do some administrative job now in our institute, and it takes many, many times. I hope that one day it will be finished with it, but in any case. So, if I will not spend all of this time, we can just discuss some questions, and I will be very happy to answer to all of your questions about oysters or other bivalves, or maybe about some questions of Russian Mesozoic, Cretaceous, or Jurassic geology. I work mainly with Cretaceous geology of Russia. So, and now I will start with my talk. Okay, let me introduce myself. You know all of me, but I use many of materials of my students. This is Igor Kosenko. He is my student since 4 years, and this June he entered to PhD study in our university. So he go to he continue with science, and he will do his PhD research in our institute also with oysters. And we work with him in big collaboration. So I need to say some words about him too. Even in Thailand in 2018, I also used our common results. So this collaboration is already 4 or maybe more years old. And now about evolutionary history of oysters and the significance for geological studies. I mainly focus on significance of oysters, how we can use these bivalves to resolve geological problems. And firstly, what are oysters? Oysters, we all know oysters because sometimes we eat them, and in Asia, in Russia, in China, in Europe, and in America, all we know, for example, Chrysostrea gigas. These oysters originally lives in Japan Sea, and his north area cover even southern part of Russian forest. But now these oysters are cultivated all around the world because it's one of the best for aquaculture. So here you can see oysters like food, and here this is Chrysostrea gigas, and this is some biostrom built by this species of oysters. In modern world, oysters live in most of all oceans except the Arctic Ocean. They live in Pacific Ocean, in Atlantic Ocean, in Indian Ocean, and only in Arctic Ocean they don't exist. Here I collect some photos where I work in with common material, with modern material. This is Japan Sea, this is Vladivostok, Russian southeast, near the boundary with Korea and China. This is Chrysostrea gigas in his natural population. This is a beach of Vladivostok city, and here you can see also some biostroms or oyster mass accumulations in Qingdao. This is a Chinese city located in northeastern part of China, and here you can see the attached specimens to the solid substrate. In this case, this is just a rock, and here this is a mass accumulation of oyster shells. This is all these photos were made in cities. And in many other countries you can see such scenes. I'm sure that in Thailand oysters also exist in such accumulations. I have seen such scenes in Vietnam and in Black Sea, in Crimea. So this is very, very common scenes which oysters build. And a few words about the morphological diversity of oysters. Oysters, this is a very large group of bivalves. Originally, oysters are separated from other bivalves because of the following characters. Firstly, they cemented by the left valve to solid substrate. Originally, all oysters did this. After some time, some of oyster taxa began to live in bottom substrate, for example, in clays or in something like this in lagoons. But in juvenile stage, they attach by the left valve to solid substrate. Just it can be very small, for example, just a piece of sand. But all oysters they do this. Second features of oysters is that they haven't their leg. Many bivalves have legs. They use their leg to move in the sediment or in the surface of sediment, but oysters they don't move. during their life. They just filtrate the current of water and take planktonic organisms to feed them. And here you can see the morphological diversity of different oysters. This is Cretaceous oysters from Central Asia. This is from Turkmenistan, from eastern part of Turkmenistan. This is very common in all Tethyan seas, Rastellum, the genus Rastellum. It is distributed from England in the west to the Japan in the east and to India in the south. Even in Africa, they appear in big quantity. And here, this is endemic oysters of Central Asia, but some similar species they lived in United States in America, in Texas or in southern states. And here you can see the adaptation of oysters to life in soft bottom. This model was proposed by famous German paleontologist Adolf Seelacher, which worked a lot of time with ichnology and paleoecology, and first idea about radiation of oysters was proposed by him in 1985. He also worked with the Polish scientists, and he published several papers about this problem, about radiation of oysters based on the transition to live in soft bottom substrate. There are two groups of oysters which can live in soft bottom substrates. There is recliners, this is morphological classifications, and mud stickers. Recliners, they have usual oysters which are cement to solid substrate. They have relatively convex left valve and less convex but also convex right valve, and they just attached to the rocks and live like this. After they start to adapt themselves to clays and some substrates like clays. Recliners, the first group of oysters who adapted themselves to live in soft bottom, they have a very convex left valve and convex or concave or just flat right valve. So they lie on the left valve on the soft bottom, and the main important is for them to save the commissure plane under the surface. It's very dangerous for them to sink in these clays, because if they are buried by clay, they die. And second group, this is mud stickers. This is lightweight oysters which live in clays in vertical positions. So they are like sticks in clay, and the commissure plane, yes, stay also under the surface of this sediment. And here you can see Arctostrea. This is a very similar oysters to Rastellum, which I show you here. This is Lopha. This is or Lopha-like oysters. This is also a large group of oysters. Real Lopha sensu stricta appeared in Cenozoic, but similar oysters also lived in Mesozoic since the Triassic period. This is boulder shaped. This is a good example is Crassostrea gigas. The oysters I already shown you in plate with lemon, and Gryphea and Exagira. Gryphea and Exagira, this is the most common oysters for the Mesozoic period. Gryphea appeared in Triassic and lived during all the Jurassic period. They were very common in European seas, in Russian seas, in Central Asia, and I'm sure that if in Thailand it will be good conditions for Gryphea in the Jurassic rocks, you can find Gryphea also in Thailand. And second, this is Exagira. Gryphea was successful during the Jurassic, and they disappeared in the end of Jurassic in the boundary with Cretaceous. And in this time, the most diversified group of oysters began to be Exagirine oysters, this subfamily which have coiled umba, but in general the shape of shell is very similar to Gryphea. This is also recliners. They have very convex left valve and flat or concave right valves. And as a group of oysters, this is mudstickers. They flourished not in Mesozoic time. They began to flourish in Cenozoic time. So this is more recent morphological adaptation, and the only exception is oysters deltoideum, which were common in the end of Jurassic in Europe, in Russia, and in Nearest East. The most known species is Deltoideum delta. This species is even figured in the explanation of first geological map in the world. It was made by English geologist Smith in the beginning of 19th century, and he described and figured oyster Deltoideum delta, which he found in Kimmeridge clay in England. Some other pictures of morphological diversity of oysters, and this is other exagirines, also from Central Asia, and here you can see modern Crassostrea gigas. And one of the problems with oysters taxonomy, of low rank oyster taxonomy, is the modification variability. Usually bivalves have relatively stable shape of shell, but oysters, because they attach during their life to solid substrate, they often are very morphologically diverse. It links with their mode of life because they are attached, and if there is not enough place, they change their shape. Oysters, in this point of view, they are very similar to trees. It's different to find two specimens of trees with exactly the same shape, and oysters, they are similar in this case to trees. You can see that this Crassostrea is very convex, and the shape of shell is very irregular and sometimes very different from the original common shape of shell. The common, this is here, and here, and here. This is also a relatively common shape. And here you see how they are attached to solid subjects. In this case, this is not rock. This is a shell of bivalve. Here, large. This is Mytilus. This is also very common bivalve. We also eat them, use like a food. And here, this is Septifer. This is smaller bivalves, also similar to Mytilus. Okay. And now a few words about shell morphology of oysters. Despite the fact that the variability of their shells is very, very high, we need to study some stable characters to classify them and to use like diagnostic characters. And here you can see the main characters of oyster shells. The most important characters, this is inner characters of their shells, because they doesn't depend from the environment. If the outer features like sculpture or outlines of shell strongly depend from environment, the inner features, they are more stable. They are correlated with internal structure of oyster soft body. For example, the shape and position of posterior adductor muscle strongly correlated with shape of heart or the digestive system. And the most important for high-rank taxonomy is a combination of features, not one feature, not one character, but combinations of them. Because when we have the combination of characters, it's more easy to group different taxes in large groups, and they are more independent compared to single characters. The most important are the hinge structure. Here you can see 5 main types of Oysters hinge structure. This is a picture of Nika Malchus. This is the world-known expert on oyster taxonomy, geology, stratigraphy, ecology. I have been in his institute. This is Miguel Cruzafon Paleontological Institute in Barcelona, and he still works. He's relatively young. He's a little bit more than 55. And he's probably the best specialist in oysters in present time. He separated 5 types of oyster hinges. First, this is asteroid type, this is easy type. You see, this is just usual ligamentaria. Second, this is gyrosteroid type. You see that in this type, the umba is a little bit coiled. Third type, this is turcosteroid type. Umba is coiled, and one of the buriliet, this part is modified. Fourth type, this is exogyroid. This is the ligament structure is completely modified. This is the most evolutionary advanced type of oyster hinge. Unfortunately, all exogyrids disappear in the end of Cretaceous together with dinosaurs and other Mesozoic representatives of Mesozoic fauna. And the last, this is griffoid type of hinge. This is like a beak, so the coiling is not in vertical axis. And here you can see the other morphological characters of oysters. Here, this is 3 different subfamilies. In the upper part, this is Pycnodont. If this is Figrea, this is Pycnodontine oyster from Tanetian of Crimea, a good example of Pycnodontine morphology. Here, this is modern Crassostrea. I told already about this species, and this is Jurassic, late Jurassic Pernastrea, Griffid oyster from northern Siberia. Oysters during Jurassic and Cretaceous existed even in northern Siberia, where in present time this is Arctic tundra and only white bears. And few words about history of classification of oysters. Oysters were known since long time. When paleontological study began, oysters were described by many authors, such for example, classics of paleontology like Sowerby or Arbigny from France. Sowerby, this is from England, or Russian paleontologist, German paleontologist. All paleontologists who work with Mesozoic, they described many species of oysters. However, their taxonomy and classification was very non-developed and very chaotic. First, who resolved some problems of oyster taxonomy, oyster classification, was Soviet paleontologist Oleg Stepanovich Vyalov. In 1936, he proposed first classification of oysters. He used the following characters. The most important for him was shape of upper or right valve. Also, he used general shape of shell, and he divided family Astridae to 4 subfamilies. First subfamily, this is Astrinae. Astrinae of valve include oysters with convex left and right valves. Griffinae subfamily includes oysters with very convex right left valve and flat right valve, and with coiled umba in vertical axis, in vertical plane. Subfamily Laphine cover oysters with radial sculpture, and subfamily Exogerini include oysters with also coiled umba, but in the plane of valve commissure. It was a big progress in oyster taxonomy. Also, Oleg Vyalov introduced many new oyster genera. Most of them are used until now, but his classification was not natural, and many problems were unresolved. One of the main problems, this is gomeomorphism, the typical feature of oysters. Different phylogenetical line of oysters start to develop similar shape of shell in similar environment, and this is a big problem in oyster taxonomy. It was problem in the beginning of 20th century, and this problem are close to be resolved only now, when we can use genetic characters like DNA, microstructure, study of microstructure, and accumulate all knowledge about fossil and recent oysters, which we collect during 300 years of oyster study. Second and very important work, it was work of Henryk Stenzel. This is American paleontologist which was born in Poland. Originally he is Polish. He was an author of Treatise of Invertebrate Paleontology. This book was published in 1971, and this is a classic book which every person who studies oysters needs to have in their tables, in their work table. His taxonomy, he resolved the problem of not natural taxonomy. He started to use complex of characters. He integrated data about ontogenetic development of oysters from larva to adult organism. He used many microstructural data, and he also used usual morphological data and focused on internal characters of oyster's body. He was one of the first who shows the link between morphology of inner surface of oyster shells and the soft body. Of course, he wasn't first, but he was first who paid the strongest attention to this. And in his classification, superfamily Ostraceae was subdivided in family Griffeidae, with subfamilies Griffeini, Pycnodontini, and Exogerini, and family Astreidae, with subfamilies Astreini and Laphini. Family Astreidae, this is unite mainly Cenozoic and recent oysters, and Griffeidae, this is mainly Mesozoic oysters, some of them preserved until now, but they are less diverse in present time compared to Astreidae. And here in the right corner of this slide, you can see modern taxonomy of oysters. This classification was published in 2018 by the team of malacologists leading by Joseph Carter from United States of America, but the person who did the recent classification of oysters, it was Nicholas Malchus from from Spain. Originally, he is also not Spanish, he is German. And here you see some new introduced subfamilies, for example, family Arctostriidae, family Ligmidae, family Flamingostriidae. This taxonomy is a little bit more complex than taxonomy proposed by Stenzel. But in general, this taxonomy follows the taxonomy of Stenzel. Few words about geological history of oysters. First fossil oysters appeared in Triassic deposits. The interesting point of view is that most of modern oysters, they live in medium latitudes or in tropical latitudes or in equatorial latitudes, but no oysters doesn't live in high latitudes like Arctic seas, Arctic Ocean, or seas of Pacific close to Arctic Oceans. And an interesting point is that in Triassic, first oysters appeared in Arctic realm. So here you can see one of the earliest fossil oysters known. This is a photocopy from Stenzel. This is representatives of the genera Gryphea. All of these oysters have been found or in Russian Arctic, in extreme northeast of Russia, northeast, this is farthest Russia, like Chukotka, this is Arctic Ocean, or in Canada, also in Arctic areas. So you can see the most ancient oysters. And this is from, I think, yes, this is from Carnia. So this is the lowest stage of Upper Triassic. The other interesting point is that approximately in the same time appeared not one phylogenetical line of oysters, but several. You already have seen Gryphea, and here you can see the other very well sculptured, radially sculptured oysters, which appears approximately in the same time, also in Triassic, and many of them have been found in Canada. So this fact, the appearance of different branch of oysters, some scientists interpret like the polyphyletic origin of this superfamily. And here you can see the third phylogenetical line of one of the most early oysters in geological history. This is Lestrine oysters. This is flat, non-sculptured oysters. They also appeared in Triassic and starts to be very common in early Jurassic. In early Jurassic, they already spread in different continents and was very successful also branch of this superfamily during Jurassic. And here I will show you some important points of geological history of oysters. How I already told, the earliest oysters appeared in Triassic, in Carnian stage of Upper Triassic. No one don't know the ancestors of oysters. This is a question which is not resolved until now. There is some hypothesis. I will not take time to explain them, but until present day, no one don't know clearly who was the ancestors of oysters. So, beginning of late Triassic, oysters appeared. In the early Jurassic, they spread themselves, and oysters started to be the common element of thanatocynosis, arctocynosis, of fossil biocynosis of marine benthic fauna. In Jurassic, already first exogyrin appeared. Some scientists believe that exogyrins appeared from Gryphea, but maybe it's possible that it was also transitional taxa, transitional genera between full graphea, usual graphea, and clear exogyreans. In the end of Jurassic, graphenes disappeared. Grapheinae, this subfamily, was the most common subfamily in Jurassic. So in Jurassic seas, graphea and similar taxa dominated all oysters biocenosis. And in the beginning of Cretaceous, first pycnodontine appeared. I will say a few words about this a little bit later, because I have a publication devoted to this question. This is a very interesting fact. Pycnodontine was descendants of graphea. During the Cretaceous, it was documented a very interesting event in oyster evolution. This is diversification of exogyrean oysters. It appears in Cenomanian, in fact, in transition from the early Cretaceous to upper Cretaceous. But exogyrean starts to be worldwide spread during the earliest late Cretaceous in Cenomanian. Probably it's linked with marine transgression, so many environments favorable for this subfamily appeared, and we document the radiation of exogyrean oysters. In the end of Cretaceous, there is other very interesting event. I think that the late Cretaceous was the best time for oysters. I was in Crimea, and in outcrop, in one layer, I found maybe 10 different taxa of oysters. In modern environment, we doesn't have such environments where we can find more than one or two species of oysters. In the late Cretaceous, oysters was so diversified and so different from each other, and we can find many different taxa of oysters even in one bed. But in the late Cretaceous, two subfamilies of oysters dominated in Cretaceous sea disappeared. These subfamilies are exogyreans and paleolaphids. This event actually correlates with disappearance of dinosaurs and other well-known marine and non-marine animals. For example, ammonites and belemnites also disappeared in this time. This is quite interesting. Probably it also links with change of environment in epicontinental seas. And Cenozoic, this is a time of modern oysters. So during the Cenozoic, recent taxa of oysters started to dominate in seas and marine and even brackish water environments. So this is the main steps of oysters evolution. And now I will focus on geological significance of oysters. I will provide several examples. Some of these examples, this is our jobs where I participated, and some examples, mainly it concerns with isotope geochemical studies. I will introduce a very interesting works recently published by other Western researchers. Main problem is that isotope geochemical studies, this is a very expensive, and you need to have a very good machines, microscopes, and other things to do such research. And most of this research are made in collaboration between scientists from different countries: Belgium, United States of America, China, or something like this. Okay, let's start. Oysters can be used and important in, firstly, stratigraphic studies, secondly, paleoecological interpretations, thirdly, phylogenetic studies, fourthly, paleogeographical studies, also as makers of sediments. They build oyster reefs, oyster biostroms, and I already show you some modern and recent examples, and isotope geochemical studies. Why oysters are so important for isotope geochemical studies, I will say you a few words now, because the skeletons, the shells consist of calcite. Usually they have very thick shell, and calcite is better preserved under diagenesis. So we can have primary isotope and geochemical record compared to other organisms which have their shells, which build their shells from aragonite. This is many other bivalves, ammonites, other cephalopods, and comparable with oysters, Mesozoic organism. For isotope geochemical studies, this is only belemnites. Belemnites, they have a very large rostrum, and they are also very useful for isotope and geochemical studies. A few words about using of oysters for stratigraphy. Oysters are not used in zonal stratigraphy because of the lower temps of their evolution compared to cephalopods like ammonites or belemnites, or quickly evolved group of bivalves such as buhyids, which are very useful for late Upper Jurassic and Lower Cretaceous stratigraphy, and inoceramids, which are one of the best stratigraphical markers for Upper Cretaceous. However, usually stratigraphical distribution of oyster species cover several geological stages. We are very lucky if the species of oysters exist, for example, only one stage, but usual species appear, I think, 2, 3, or 4 stages. In many cases, this is also very helpful when we doesn't have any significant for stratigraphy groups of fossils. And like exceptions, some species of oysters, this is really a good marker for stage, but mainly this is exception. And some examples of using of oysters in stratigraphical studies. Here, this is example from my PhD work, PhD thesis. I studied late Jurassic and early Cretaceous oysters from Russian Arctic, Northern Siberia, and Northern Urals. And there were some taxa which really have a very narrow stratigraphical range. Also, we can see clearly the evolution of the shape of shell. These examples are Deltoideum, Bareodeltoideum preanabarensis. This is a good indicator for the Volgian stage in Northern Siberia, and Deltoideum, Bareodeltoideum anabarensis. This is a very good indicator of Piracean and Belanginian stage in Northern Siberia. However, these species are not very largely distributed, but for Siberia and for Urals, they can be used like markers for correlation. This is also a very wide territory, covers, I think, the territory more than one France or Spain or Germany. This is quite large territory. And the other example, this example are more classic and more common. This is Paleogyra virgula. This is a very well-known species of oysters, one of the first common exogyrin oysters, largely distributed in late Jurassic sediments of Europe, a Russian platform, Nearest East, and this is a good indicator of Kimmeridgian stage. However, it can be also found in Oxfordian and Volgian stage, but mass occurrence appeared in the Kimmeridgian stage. And here is an example. This is oyster shell bed from the Boulogne section in northern France. This is the other side of Channel Sea, French coast of Channel Sea. Also, oysters are sometimes very useful for paleobiogeographical studies. Here I will show you an example. This is a figure from the master thesis of Igor Kosenko. I already told this is my student, and this is the stratigraphic distributions of oysters in Central Asia, in Turkmenistan. In these green quadrangles, this is endemic species. So there are many. Most of oyster species, I will note, I'm noting now, they're cosmopolite. So they're distributed in northern hemisphere, in southern hemisphere, and you can find them in Europe, in Africa, in Asia, in North and South America. But in several regions, probably isolated, a bit isolated from neighboring territories, some oyster phylogenetical lines started to produce endemic taxa. For my point of view, the best indicator for paleobiogeographical reconstruction, this is not the level of species, but the level of genus, because this is very difficult to differ some species, very close species of oysters, but genera you can easily differ from each other. And here we can see that there are some endemic genera like Pseudogyra, like first species of Costagyra, and also some endemic species. So we can do some conclusions that this territory was a bit separated from other territories during this period. And also this is not only element of fauna who demonstrate such model, also some ammonites and echinoderms from this region. They're also different from similar groups of fauna of neighboring areas. So a good example of using of oysters for paleobiogeographical studies. As an example, this is an example published by famous South African paleontologist Mike Cooper. He works a lot with South African oysters, and he described many endemic South African genera, such Utrabica strion, Velostrion, and Zulastrea. These genera, they are really very different from other similar genera, and we can do a conclusion that South Africa in South Africa it was special conditions. Also it was quite isolated region from Tethys Ocean. So this is a good example for the using of oysters for paleobiogeographical reconstructions. And few words about paleoecological interpretations and use of oysters for paleoecological reconstructions. This is a part of our presentations with a colleague from Moscow. His name is Alexey Politov. He works in Geological Institute of Russian Academy of Science in Moscow. We study with him a collection of oysters collected from the Kilovian deposits of western part of Russian platform. This is the Fokina quarry. You can see that this region is not far from Belarus and Ukraine. So this is the western part of Russia. And here this is a section, a field note of a field figure of section made by Alexey Politov. Most of the interesting point is that this is clays, and clays. So this is fully clay section, but an interesting point that in some layers there are mass occurrence of oyster shells. So sometimes there is even bridge made from oysters shells. It was a very interesting object for paleoecological reconstructions, and we did small research based on this collection. The oysters was, this is Gryphea. Gryphea is the most typical oyster for Jurassic. And here you can see the life position of these oysters in soft substrate. So you see that the convex left wealth is submerged in this clay, and the upper wealth or right wealth and commissure plane is under the surface of this substrate. This is a typical example of recliner, this group, morphological group, about which I told in the first part of my talk. Okay, now we just need to remember that these oysters, they were in such position during their life. And the interesting point of view that many of oysters from this collection, they have traces, the boring traces or organisms and clusters in their shells. And we can study the distribution of boring traces and organisms in clusters in their shells to make some conclusions about their taxonomy, how they were transported after their death and before their burial. And here you can see good examples of organisms and clusters in these shells. So one of the common organisms, this is other oysters. This is Nanagironana, small exogyrin oyster. You can see it in written by letter N, and Deltidium delta. I already told you about this species. Here, this is Deltidium delta. And you can see that these encrusters, they're distributed in both sides of left valves. I mean the outer side and the inner side. And this is obvious that in inner side, this organism cannot settle during the life of these oysters because there was a soft body and these organisms cannot introduce themselves to this cavity. So we can make a conclusion that this settlement was made after the death of this bivalve. Second example, we see that these organisms and clusters, they are also found in the outer part of shell. And the interesting point of view that we see serpulids, this is calcite worms which made the skeleton like a tube. This is a typical marine worm which we can find in modern communities. And they appeared in the most convex part of shells of Gryphea. It means only one. It means Igor, come here. This is I will introduce you. This is Igor Metelkin, my student. He worked with me and he did part of this job, which I demonstrate to you. Okay. We can make only one conclusion that their shells they were transported after their death. I will show you the proposed model a little bit after. Here we see that these worms, serpulids, they also have orientation in shells of Gryphea. It probably means that it was a current which appeared during the life of these worms when they build their skeletons. Okay, these serpulids are called Philogranular uncinata. All determination of serpulids was made by Alexey Politov. He is a specialist on this group of tube worms. And this is the other example. Here we can see the boring traces on the shells of Gryphea lucerna. This is the same shells from the same horizon from the Fokina quarry section. And what we can see here, we can also see that the boring traces are distributed in both sides. Some of them, they appeared in the outer side, and some of them appeared in the inner side. And sometimes we even can see the remains of the borer clump in the borer trace. This is marked by the star, small star in the figure in the right corner of the photo table. So these boron traces, they can also give us some ideas about the taxonomy of these bivalves, and also we can reconstruct some animals which lived together with oysters, but they didn't have skeletons, and we can know about them and only based on the boron traces, ichnofossils. And here is photos of these organisms who produced this boron trace. This is a very special type of marine invertebrates, pharanids. They don't have skeleton, and they just have soft body. Very rare animal, not a lot of species, but they appear until now. Here, this is a recent borer polychaete, Polydora brevipalpa. This is a parasite worm, polychaete worm, which lives in shells of modern bivalves. And here you can see the gastronomic bivalve, probably from aquaculture. This is picten. Very tasty too, maybe even better than oysters. And this parasite borer polychaete worm. And in the right part, this is borer clam gastrochena. They appeared in Jurassic, live until now, and they live in thick shells of animals or in rocks. And here, this is a model of taphonomical model of burial process of these shells of Gryphea. All of these taphonomical and paleoecological features allow us to reconstruct and propose this model. Here you can see stages of transportation and burial of Gryphea shells. First, this is just Gryphea in life position. Second, what happens with these animals after their death? This is disintegration of valves, and so the ligament of these oysters is not very strong, and after the death, this is organic ligament. It starts to be weak. The force which unite the right and the left valve of this oyster starts to be very weak. So the light valve go out from the original position. The third point is we see how these organisms and clusters settle to the inner surface of these valves. Fourth, what happens with this shell? This is overturning of heavy left valve. It can be made by storm events, and this valve became to have a stable position on surface. So it starts to be, the convex side starts to be like outer surface. The fifth, what happens, this is a settlement of other clusters and boron organisms. This is other oysters and boron worms, pharanids, and other interesting animals. And the last, this is burial under the sediment. So using this paleoecological and taphonomical feature, we can reconstruct the taphonomical and burial history of these shells. And now I will speak about phylogenetical studies. First case, it will be a case of pycnodontine oysters. Pycnodontine oysters is a very interesting group of oysters. They have not usual features compared to other oysters. They're relatively stable in their morphology and their microstructure. First who separated this subfamily was Stenzel. He did this in 1959, and he provided a diagnosis You can see it here. I will read. Commissural shelf well defined, delimited proximally by circumferential curve. Hamata short to long. This is a very important features of this oysters hamata, even if they develop in different branch of these bivalves. And also an important feature, the most important maybe, is vesicular shell structure. A vesicular shell structure, this is a very specific shell structure which can be easily investigated by optic microscope in cross sections. And here you can see an example of this vesicular structure. So this is a porous structure which is very specific for this subfamily. The genus Pycnodonta, the type genus of this subfamily, was described from Crimea. It was made by Russian paleontologist Fischer von Waldheim. Originally he was German, but many different people worked and lived during 19th century in Russia. So it was described in Crimea. And after Pycnodontines have been described in many other places around all of the world, in Northern America, in South America, in Africa, Europe, Asia, everywhere, even in Australia. This is a very diversified and interesting subfamily which flourished during the late Cretaceous and beginning of Cenozoic in Paleogene. Some recent representatives, recent species of this subfamily also exist in Indian Ocean, in Atlantic, and in Pacific Oceans. And the interesting point of view, it was the origin of this subfamily. Stenzel, who first described this subfamily, believed that the most ancient species was Texigryphea. This is a very specific Pycnodontine species from the Albion of southern states of United States of America, e.g. Texas or Oklahoma. But the interesting point of view, the interesting point was that this genus is very different in their morphology from typical Pycnodontis. Also, many of Pycnodontis are known in the uppermost lower Cretaceous in Europe and in Central Asia. So it's hardly believed that this Texigryphea was an ancestor of this subfamily. So we did our investigation and proposed an alternative hypothesis about the origin of this group. In Crimea, in the middle of 20th century, there was described in numerous quantity an interesting species of oysters. Firstly, it has been described like Gryphea weberi, but further investigations show that this species have some features which is not typical for Gryphea. It appears in Beriasian of Crimea, and I was lucky to study the microstructure and the morphology. It was a gift from famous Russian paleontologist from St. Petersburg, Tamara Bogdanova, who studied during all her life Middle Asian and the European early Cretaceous bivalves and ammonites. So we did an investigation under the microscope of this very relatively well preserved collection of oysters. And here you can see the schematic sketch illustrating shell morphology of this species. You can see not typical for Gryphea hamata. I already told you that hamata is a typical feature of Pycnodonta, and other features are quite common for Gryphea too. So another taxonomical and other morphological characters. This is quite similar to Gryphea. And this is a map showing the locations of places where these species have been found. And here you can see the photo table illustrating the morphological characters of these species. This species is really very similar to Gryphea, but how I told you, it demonstrates Hamata. This is evolutionary advanced character, and this is absolutely not typical for Gryphea. After we study the microstructure under the light microscope, and the microstructure, we found that it's quite diverse, but very similar to microstructure of Gryphea. There is no vesicular structure typical for Pycnodontis. And if we take only the microstructure, this is typical Gryphea. Okay, which conclusion we can do after this study? It means only one, that this species, it was a transitional taxa between subfamily Grypheans and subfamily Pycnodontines. So this is the missing branch between these subfamilies, and it was divided in separate genus Pycnogryphea. Here you can read some conclusion. So the main idea is that this species combine evolutionary progressive character such as Hamata and microstructure of typical Gryphea. So microstructure, this is archaic, and morphological characters, this is advanced. So this is an interesting example which unite evolutionary advanced and archaic features. So this is a link between Grypheas and Pycnodontines. We put this taxa in the subfamily Pycnodontines because of Hamata. I think that we should divide the subfamily using this, not only this, but mainly this taxonomical character. And few words about other taxonomic studies. How I told you already, the microstructure of oyster shells play a very important role for determination or for differentiation of different taxa. Gamiomorphism is a very typical feature for many phylogenetical line of oysters. If different lines of oysters started to live in similar paleo environments, they started to develop very similar shells. And sometimes this is very difficult to differ different, even genera, not only species, but even genera. And I want to introduce such case. This is also Crimea, but not the lowermost Cretaceous. This is the uppermost Cretaceous. This is the outcrop of Maastrichtian strata near the Trudolubovka, near the Skalistaya village in south central Crimea. Here, the star marked the location. This is a typical, even classical outcrop, and in this outcrop you can find, I think, more than 10 different species of oysters. And one of the most enigmatic was this species. This species has coiled umber, so this is exogerine oyster, and doesn't show any sculpture. So many authors describe it like Amphidonta. During many years, it was part of the genus Amphidonta, but the genus Amphidonta have little bit different morphological characters, but the only one point how we can divorce the real Amphidonta from, for example, relatively similar genera Exagira or Rhinchostrion, this is a microstructure. For example, Amphidonta has a very specific herringbone cross-foliated microstructure, and Rhinchostrion demonstrates even more specific, even more exotic microstructure, which is called ICCF. The terminology of microstructure is quite complicated. Just it's better to don't think too much if you don't study oysters in details about this. And this is also an example of photos made by optical microscope from cross sections of these oyster shells. And what we can see this very specific microstructure, ICCF. This microstructure looks like long elongated prisms and build very thick layers in their shells. Probably it was an adaptation to special environment because this taxa is linked with special phases. This species all times found in glauconitic sandstones, so this is a very shallow environment, probably with very high hydrodynamic activity. From my point of view, my hypothesis is that this thick shell is an adaptation to make the shell heavy, to make it more stable under the high hydrodynamic conditions. Maybe someone will introduce the other hypothesis. So we found this specific microstructure, and only using this microstructural character we can do a conclusion that this is not Amphidonta, but this is homeomorphous taxa, which should belong to the genus Rhinchostrion. And this founding of Rhinchostrion, this is the this is the latest founding of Rhinchostrion in the world. So this is the latest Maastrichtian. Usually they appeared since Albion to maybe Canyasian, in the best case Campanian. So we proved that these oysters survived until the end of Cretaceous. And the last part of my presentation, the last part, it deals with isotope geochemical studies. I will demonstrate our work. We tried to do some isotope geochemical studies in our institute, but the main problem is that all of these studies, this is very expensive, and the level of such studies which we do in Russia is much lower than studies made in Western countries, in Europe or in America. And here, this is a very good and relatively recent article published by Niels de Winter with colleagues, which deals with geochemical records of oyster shells. Here they studied several specimens of widely distributed late Cretaceous oyster, Pycnodont vesicularis. This is a classic example of late Cretaceous oyster, and they did isotopical and geochemical investigation. In this picture you can see the tracks, how they did this investigation. Very important, the aim was to make ontogenetic variations of geochemical and stable isotope parameters during the ontogenetic growth of their shells. So in this case we need to do a track which starting from the beginning of oyster growth and ending in the end. This team of researchers chose the ligamentary, and this is a really good part because usually this part is well preserved. You can see the growth lines, and the microstructure is similar. If you check the other parts of the shell, the microstructure is rather diverse. Here, this is usual calcite microstructure, and this white part, this is vesicular microstructure. So this specific microstructure of pycnodons. Okay, let's see what this team conclude from the research. Also, I will say a few words about preservation of oyster shells. For isotope and geochemical studies, this is very important to understand the degree of preservation of shell, because if shell will be genetically altered, the primary composition of elements and isotope will change, and we will not use the original geochemical composition. How we use this geochemical composition? First way is to reconstruct paleotemperatures. We reconstruct paleotemperatures using the stable oxygen isotope ratio. There is two oxygen isotopes, oxygen 16 and oxygen 18, and the ratio strongly depends from the temperature of water in which carbonate of shell is precipitated. This is this conclusion based on the investigations of modern oysters. So people did an experiments and related the annual or seasonal temperature with the stable isotope oxygen composition of their shells. If you take the carbon isotope composition, this is also a very interesting parameter, but it depends from bigger quantity of factors, not only one. Isotope oxygen ratio depends also from polysalinity, and because of this we need to choose oyster shells from sections where we know or we can suggest the normal marine salinity. Good indicators for such normal salinity is cephalopods. They can live only in normal conditions, normal salinity, or echinoderms. Echinoderms, they live also only in normal marine salinity. If you take the carbon oxygen, this is quite complicated, more complicated, and mainly it depends from the productivity, organic productivity of this basin where this oysters lives. Okay, and how we can trace the degree of preservation of these shells? There are several geochemical and microstructural methods. First method is just to investigate the microstructure under the scanning electronic microscope. Oysters, they have a specific structure of aggregates of crystals, and when recrystallizations happened, we easily can see these processes. So there is aggregates of crystals which are typical only for oysters. This is the first way how we can trace the degree of preservation. The second way, this is cathodoluminescence. Cathodoluminescence, this is also under the scanning electronic microscope, and using this method we can see the parts of shell with high content of ferrum or marginates. These two elements, they are good indicators of diagenesis. So if there is a lot of ferrum, iron, or manganese, Mn, it means that the shell is diagenesis is changed the primary chemical composition of this shell. And the other method, this is also scanning electronic microscope. We just can use we can take measurements on it by tracks and measure content of ferrum or manganese Mn. So there is a few methods. This is optical. Even in optic microscope, you can do some conclusions. This is cathodoluminescence, and this is geochemical. Also, we can take samples for ICP-MS or other geochemical analyses to know the quantity of ferrum or other important elements. If the shells are enough good for research, we can take samples for elemental analysis or for isotopic analysis. And making such tracks, ontogenetical tracks, we can have such curves. This is ontogenetical curves for different specimens. And we do some conclusions, taking several specimens and integrated all of this data. And the most interesting from my point of view, this is calculation of paleo temperatures. There is several special formulas which used to calculate these paleo temperatures, and taking the isotope ratio of oxygen 16 and oxygen 18, we can calculate temperature in each point of oyster shell. So in the end, we have a track of paleoseasonality in Cretaceous, Jurassic, or other paleoseas. So such interesting method. Thank you for your attention, and if you have questions, I will be very, very happy to answer for them. Thank you. This is from Altai. This is from last expedition.
Thank you very much, Associate Professor Dr. Igor, for your interesting and useful presentation. Now the question and comment floor is open. Please feel free to ask and share your view, please.
อ่านคำถามก่อนก็ได้นะเกริ่นไปก่อน
Okay, there are a lot of questions in the chat. The first question from Mr. Narame. How are different oyster significance between freshwater oyster and marine oyster?
I'm very sorry, but please, can you repeat your question? The difference between fully marine and the brackish water oysters, yes?
Yep.
Yes, okay. From my point of view, during the Jurassic, for example, in the Jurassic time, all oysters were fully marine. So they live in epicontinental seas with normal salinity, and they didn't live in brackish water environments. There is Stenzel noted that representatives of the family Griffins, which dominates the Jurassic seas, is Stenagalin, or it means that they live in normal marine environments. So if we found a species of Griffin oysters, probably it means that we deals with normal marine environment. And brackish water, this is several taxa which adapt themselves to live in brackish waters. Really, there are some taxa. Mainly, this is crassostrean oysters. So, if we can determine the species of oysters, in many cases we can say it lives in normal marine environments or in brackish waters. Okay.
Thank you very much, Dr. Igor. I follow my two questions. The question is, in northeast of Thailand, we found the succession of the Ramstoren integrated with red-based sandstone in fertile environment, but we found the Ramstoren with a lot of oyster. What the environment of deposition of oyster is my
You found which kind of, you found Rastellum, yes?
yeah, we found the oyster in the limestone.
In limestone, okay, it can be also other problem. It can be not only brackish water, some oysters probably.
I sent you already the picture of the oyster in this area, in not of Thailand.
Yes. You sent me one time. Yes, I remember. This is quite radial sculpture. I remember. Yes. I think that this is not brackish water conditions too. This is probably normal marine environments, because this is Rastellum. This is also ancient taxa, and probably most probably this is normal marine, or maybe high salinity, but not lower salinity, not brackish water.
Okay, thank you.
Thank you for your question.
Next question from DDG. There are 3 questions. The first, how did you define the first extinction of oyster on Earth? Second, were there any evidence of break during the oyster evolution? The third, your research study on this subject is very interesting. Do you expect the result of this study to lead to other discoveries? What are your next target?
Okay. Thank you for the question. First question was about the how we define extinctions. Yes. Yes, I think about extinctions. Okay. This is a very good question, because how I told, the oysters are very sensible for special phases. So if they prefer to live in shallow marine environment with high hydrodynamics, they can be found only in such places. But to define extinctions, this is mainly based on the analysis of literature. So this is analysis of published data about oysters.
Igor? This so mine. I think the first question is that how did you define the first existing of oysters on Earth? Not extinction.
Okay. First,
not extinction.
Okay.
Sorry about that. Okay.
Okay, I just don't see the chat, and Okay, sorry for I misunderstood you. This is very interesting that first oysters, they are not very different from other oysters. So they are very similar to other Mesozoic oysters, and very different from other similar bivalves. The nearest bivalves, they cement by right valves, not by left valves, and have other morphological differences. So it's easy to define first oysters because they're very, very similar to Jurassic Gryphaeus or other Jurassic representatives. And this is easy to define from other bivalves because they really have some specific characters, such as cementations by left valve, not by right, only by left. And about the next target. About the next target, I think for me in study of oysters, this is comparative study of the microstructures under the scanning electronical microscopes to better understand the taxonomy and to develop the taxonomy, because in recent taxonomy of oysters there are still many questions, many unresolved questions, and I believe that we can resolve them using scanning electronical microscope. And this is a very developing branch of paleontology now, study of microstructures. I think that this is the most interesting direction of future studies. Thank you.
Okay, thank you. Because actually, I asked another question before the last one.
Okay.
I asked you.
Please repeat.
Were there any evidences of break during the evolution of the oysters? but I think you clearly show during your presentation.
I don't think that I will answer to this question. Actually, I don't think that there is clear breaks. There is extinctions, obvious extinctions. There is late Cretaceous extinctions, and in fact, this is the only one extinction clearly visible in oyster evolution. But there is no breaks. So taxa which start to flourish, for example, in Cenozoic, they appeared in latest Cretaceous. So they already existed, but they will not dominate species. So there is no significant breaks,
Okay.
but there is, I think, one significant extinction. Yes.
Okay. Thank you. Next question is from Ponpen Janasit.
Next question from Professor Dr. Panya. There are two questions. The first is Cretaceous the good time for oyster because the world at that time became so hot and many places, including Thailand, were deserts. The second, during mega mass extinction, any isotope anomaly occurred during that time. Did oyster show any change in morphology?
Okay, thank you for both questions. This is both questions are very interesting. I try to answer step by step about Cretaceous and why this time was so favorable for oysters. I think it was two main factors. One is that big quantity of epicontinental seas. So the best environment for oysters, this is a shallow epicontinental sea. About temperature, I think yes, temperature is also very good, hot temperature for oysters. But for example, during the Paleogene, it was climatic temperature maximum, and temperature was very, very hot too. However, the quantity of oysters was not so high like in Cretaceous. So I think mainly this is special environments, shallow water seas with normal salinity. Maybe during Cretaceous Paleogene transition, some change of currents happened or something like this. This is very difficult to answer for this question because this is usually complex of factors, not only one. But I think that the temperature, this is not the most important factor. And about second question, honestly, I cannot answer for this now because my studies are mainly focused on taxonomy, on paleobiogeography, and in stratigraphical distributions. So, and mainly in early Cretaceous. I study mainly early Cretaceous authors.
But not for the Cretaceous Tertiary, yeah?
Yes, Cretaceous Tertiary. This is a very interesting period of time, but I didn't introduce myself too deep to this problematic.
Okay.
Thank you.
Yeah. Thank you.
The next question from Dr. Ponpen. There are two questions. The first, beside the irregular surface or shape of shell, which character can we use to distinguish the oyster bivalve from the oyster fossil? Number two, your specimens are very nice. How do you extract the shell from the rock? How long does it take for the preparation? Okay, please.
Okay, thank you very much for this question. Yes, the specimens are really very good, and the answer is relatively easy. Most of them they are collected not from carbonates. Most of them were collected from sandstones or some other terrigenous rocks, clays, sandstones, labralites, siltstones, but not carbonates. I know that in carbonate rocks, the degree of preservation is much lower than in terrigenous rocks. So this is the answer for this problem. This is not a problem to collect them from sandstones, just the problem is to collect from carbonate rocks, from limestones or from something else. And how to distinguish oysters from other bivalves in rock? This is not easy. This is not easy many times. So if oysters are well preserved, this is not a problem. We just check the inner surface of valves, check the ligamentary and posterior adductor muscles, the shape and all of this. How to distinguish oyster when it is not well preserved? I think one good method is to study the microstructure, because for oysters, oysters have very specific microstructure, and you can make a cross section and study the microstructure under the even light microscope. Probably it will give you some ideas, oyster or not oyster. And also oysters, they usually have very thick calcite shells. Other bivalves usually less thick, and the third way, if you see something irregular, something ugly, this is probably an oyster too, because only oysters grows very unregularly. Not all. Some of them are very beautiful and geometrical, but some of them are very irregular, and this character means that this is probably an oyster. So something like this. Thank you for the question.
ขออนุญาตนะคะขออนุญาตthank you Igor. Hi, I'm Om. How are you? Yeah, it was. That were my question. And how are you?
This is very, very nice to hear you. I miss you with Sid.
We miss you too.
I'm okay now. I'm in Russia. I spent 2019 in China in Nanjing Institute, and I came back when the pandemic started. And I believe that I will come back to China after a few months, but I'm still here, and my clothes and my documents are still in China. So, yes. But in other cases, this is all good, so it's okay. And how are you?
I'm fine, except COVID-19. But yeah, we stay safe at the museum. I'm still working at the museum now, and part of my question, I want to ask you more about the microstructure study. Can it be applied to other bivalves for phylogenetic analysis?
Yes. Yes. This is microstructure is a very important feature for all bivalves. Just it's very complicated to understand all of this terminology and all of these differences. Because I spent 1 year to understand the stratigraphy Cretaceous of China and the Russian Far East, and I spent much more than 1 year to understand the terminology of oyster microstructure. So you need to spend probably half of your life to to resolve such problems. You need to be really specialist on microstructures.
Okay.
But there is some
papers,
yes,
book. Okay,
which can be helpful to you. This is a recent treatise, Carter and others. I think this is 2011. Carter and other treatise of bivalves. I have this book. If you want, just I can send you in your email.
Sure. Thank you. Because as Mr. Naramed said that we found some that we thought that it is oyster, so we can check from the microstructure if it's oyster or not, right?
Yes. Just I need to also to say that cross section should be very well prepared. Maybe firstly, this is better to study under the light microscope to make some photos, and after to study by SEM. So it will give some ideas.
Okay. We need more knowledge about the preparation and this method. So if you can suggest us, very good. Thank you.
Thank you. Just let's be in touch. I think in Facebook I can send you.
Sure. Yeah, we follow together.
Yes. I check you. We see that. Enjoy by your.
Very glad that you are fine.
Yes, and for me this is a big pleasure to hear you, and I hope we can meet in nearest future somewhere when the pandemic will be finished.
Yeah, maybe in China next time.
Maybe
in Nanjing, maybe.
Yes.
Okay, thank you, Igor.
Thank you. Yes.
Okay, Naramed. Because of in Thailand we have found oyster in many places, and from your experience, what that your suggestion that just start for the project to study the oyster in Thailand? From your experience, how to start for study the oyster in Thailand?
Suggestion. Honestly, I think that in Thailand, if you have oyster in carbonate, this is better to firstly don't think too much about isotope geochemistry, because it's probably the microstructure and shell is poorly preserved. But I think that the good way is to collect all the bivalves, and not only oysters, and to study complex all the assemblages of bivalves. Oysters, I'm sure they will provide something important even for stratigraphy. Firstly, collect the collection, and after to study it with other bivalves, of course with other and other groups of fauna. All what can be found will be useful, I'm sure about this.
Okay, maybe next time, maybe invite you again to lecturer for correct the sample for mature section, or make the biostratigraphy of oyster, something like that.
I'm sorry, I didn't understand the beginning of this. What? Please repeat the beginning.
Maybe next time, maybe I invite you again to talk about for correct the sample from fields, mature the section, prepare the sample, or something like that.
Oh, it will be a great pleasure for me. So I'm all time open for such ideas and collaboration.
Okay, thank you.
Thank you.
Okay, thank you very much, everybody, for your question and comments. Ladies and gentlemen, before the end of the DMR special talk today, I would like to invite Dr. สมหมาย เตชวาล I would like to invite Dr. สมหมาย เตชวาล to deliver a thank you speech to our speaker. Please.
Yes, Igor and everyone. I try not to be so formal, but okay. But this is the good time for DMR and for the technical people from Thailand to listen to your talk. It is very useful for the research in geology and paleontology in Thailand, and we have the chance, to hear from you, and also to exchange some information and knowledge about the evolution of the oysters, which I think it is the good evidence for stratigraphy study in Thailand and also in other regions of the world. Last but not least, I would like to convey our sincere thanks to you, and also to your team, and also the team of IGCP, which you are working on. And I hope that you will come to have a talk with us, to give the presentation, a very good presentation like this, when you have the progress on your work. And also we probably have some cooperation between your university and also with the DMR in the near future. Okay, thank you very much, Igor.
Thank you very much to all of you. It was a big honor for me to be invited to this meeting, and I'm very happy to see all of you and to listen, to hear old friends from Thailand. Yes, thank you very much. Thank you.
Thank you. Thank you. Thank you.
Thank
Thank
you,
you very
Igor.
much, Dr. Somat Yuchawan and Dr. Igor. Finally, the DMR special talk has come to the end. On behalf of the organizer of today, I would like to say thank you to all of you for your sharing knowledge and experience. See you again next time. Bye bye.
Bye.